I'm sure you've heard the news. Humanity needs to master thermal energy to become a Type 1 civilization on the Kardashev scale. Have you ever wondered what makes things hot or cold? The answer is thermal energy. Thermal energy is the total energy of all the tiny particles that make up an object. The more these particles jiggle and move, the hotter the object feels. We can understand this better by thinking about gases. Gases are made up of tons of tiny molecules that are constantly zipping around and bumping into each other. This movement is what we call kinetic energy, the energy of motion. The faster these molecules move, the more kinetic energy they have, and the hotter the gas becomes. Pretty cool, right? Let's dive deeper into how this works. Imagine a room full of bouncy balls constantly in motion. They bounce off the walls, the floor, and each other, creating a chaotic yet fascinating dance. That's kind of what it's like inside a gas. The molecules are in constant random motion, colliding with each other and the walls of their container. Each molecule has a certain amount of kinetic energy depending on how fast it's moving. Some move quickly, while others move more slowly. We can actually calculate the average kinetic energy of these molecules using a special equation. Average kinetic energy equals 3/2 times K times T. This equation helps us understand the energy dynamics within the gas. Now, don't let this equation scare you. It's simpler than it looks. It just means that the average kinetic energy of the molecules, how much they are jiggling, is directly related to the temperature, how hot or cold it is. The hotter it gets, the more energetic the molecules become. The K in the equation is a special number called Boltzmann's constant, which helps us connect energy and temperature. It's a fundamental constant in physics. Let's say the temperature is really high. Imagine a scorching summer day. That means our bouncy balls are bouncing around like crazy. They have a lot of energy and move very quickly. High temperature, high kinetic energy. The molecules are zipping around at high speeds. If the temperature drops, the balls slow down. Think of a chilly winter night. Lower temperature, lower kinetic energy. The molecules move more sluggishly. It's all connected. The temperature directly influences how energetically the molecules move, creating a fascinating interplay between heat and motion. But wait, there's more to the story than just kinetic energy. Molecules also have potential energy, which is the energy stored in their bonds. Think of it like holding hands. When molecules are close together, they hold hands tightly, like in a solid. They have strong bonds and low potential energy. As things heat up, the molecules get more energized and start to loosen their grip. They might transition from a solid to a liquid, like ice melting into water. This requires energy to break those bonds, increasing their potential energy. Let's take water as an example. When we heat liquid water, the molecules move faster and faster. Eventually, they have enough energy to completely break free from their bonds and become a gas, water vapor. During this phase change, the potential energy increases significantly. Now, how do we keep track of all these energy changes? Scientists use a handy tool called a Mollier Diagram. It's like a map that shows us how energy changes with temperature and pressure, especially during phase changes. For water, the Mollier Diagram shows distinct regions for ice, liquid water, and water vapor. As we add heat, we can follow the path of water as it transitions between these phases. The steeper the path, the more energy is required for the change. The Mollier Diagram helps us visualize the energy involved in processes like boiling water or freezing ice. It's a powerful tool for understanding how energy and phase changes are related. Section 5. Passing the torch. Understanding conduction. Now that we understand how energy is stored within objects, let's explore how it travels between them. This journey of energy is crucial in many everyday processes and scientific applications. One way energy travels is through conduction. This is a fundamental concept in physics and engineering, playing a vital role in everything from cooking to industrial manufacturing. Conduction is like passing a torch. Heat energy is transferred from one molecule to the next through direct contact. This process is essential for understanding how heat moves through different materials. Imagine holding a metal spoon in a cup of hot chocolate. The heat from the hot chocolate travels up the spoon, making it warm to the touch. The heat from the hot chocolate makes the molecules in the spoon vibrate faster. These vibrations are the key to understanding how conduction works. These vibrations then pass along the spoon, from molecule to molecule, until the entire spoon feels warm. This chain reaction of vibrating molecules is what we call conduction. The rate of heat transfer through conduction depends on the material. Different materials have different abilities to conduct heat, which is why some objects feel hotter or colder than others. Some materials, like metals, are excellent conductors because their molecules are tightly packed, allowing for quick energy transfer. This is why metal objects heat up quickly when exposed to a heat source. Others, like wood or plastic, are insulators because their molecules are farther apart, slowing down the heat transfer. Insulators are used to prevent heat loss or gain, making them essential in building materials and everyday objects. Scientists use a formula called Fourier's law to calculate the rate of heat conduction. This law helps us understand and predict how heat will move through different materials under various conditions. It tells us that the rate of heat transfer depends on the temperature difference, the material's conductivity, and the area of contact. By understanding these factors, we can better control and utilize heat in various applications, from cooking to industrial processes. Section 6. Riding the heat wave. Exploring convection. In this section, we will delve into the fascinating world of convection, a key mechanism of heat transfer that plays a crucial role in various natural and industrial processes. Another way heat travels is through convection. This process is essential in understanding how heat moves through fluids, whether they are liquids or gases. Convection happens when warmer, less dense fluids, like liquids or gases, rise, while cooler, denser fluids sink, creating a circular flow. This movement is driven by the differences in density caused by temperature variations. Think of a lava lamp. The wax inside heats up, becomes less dense, and rises to the top. As it cools down, it becomes denser and sinks back to the bottom, creating a mesmerizing cycle. Natural convection happens because of density differences caused by temperature variations. This phenomenon can be observed in many everyday situations. For example, when you boil water, the water at the bottom heats up, becomes less dense, and rises. This rising hot water is then replaced by cooler water from the top, which sinks down to the bottom. Cooler water from the top sinks to replace it, creating a convection current. This continuous cycle ensures that heat is evenly distributed throughout the fluid. Forced convection is when we use external forces, like fans or pumps, to move the fluid and enhance heat transfer. This method is commonly used in various applications to improve efficiency. Think about the fan in your oven. It circulates hot air to cook food more evenly. This ensures that your meals are cooked thoroughly and consistently. We can calculate the rate of heat transfer through convection using a special equation that considers the fluid properties, flow rate, and temperature difference. This equation is vital for engineers and scientists working on thermal systems. This helps engineers design efficient heating and cooling systems. By understanding and applying the principles of convection, they can create systems that are both effective and energy efficient, ensuring comfort and sustainability in various environments. Section 7. Energy from afar. The power of radiation. Finally, heat can also travel through radiation, electromagnetic waves that carry energy. Unlike conduction and convection, radiation doesn't need any matter to transfer heat. That's how we feel the warmth of the sun, even though it's millions of miles away. Everything around us, including our own bodies, emits thermal radiation. The hotter an object is, the more radiation it emits. We can feel this radiation as heat, even if there's no direct contact or fluid movement. A very important law called the Stefan-Boltzmann law helps us calculate the amount of heat radiated by an object. It tells us that the radiation emitted is proportional to the fourth power of the object's temperature. That means even small temperature differences can result in significant changes in radiated heat. Section 8. Tying it all together. Thermal energy in review. So there you have it, a whirlwind tour of thermal energy. We've learned that thermal energy is all about the kinetic and potential energy of tiny particles. The way these particles move and interact determines an object's temperature and its state of matter. We've also explored the amazing ways heat travels: conduction, convection, and radiation. Each mechanism plays a crucial role in our everyday lives, from cooking our food to keeping our homes comfortable. Understanding thermal energy and its transfer mechanisms is key to comprehending how our world works. So keep exploring, keep asking questions, and never stop learning about the fascinating world of science.